Involving absolute value. First, we're going to look at solving and graphing absolute value inequalities that use a less than sign, and then solving and graphing absolute value inequalities that use a greater than sign. It makes a difference when you have absolute value brackets, whether you've got less than or greater than. It's going to come out looking real familiar. I think when we're done, although there will be some quirks as we go through using inequalities, or using absolute value. I want you to think about this first statement. The inequality x, the absolute value of x is less than 3, means that the distance between x and 0 is less than 3. Because what is absolute value again?
The distance from 0.
Absolute value is the distance from 0. So when you think about the absolute value of x, that just means the distance that x is from 0. And so when you say the absolute value of x is less than 3, it just means that x is less than 3 units away from 0. And so if we were going to graph that, we would have to think, first of all, x could be to the right of 0, a distance up to but not including 3, right? And then we also have to think about that x could be this distant direction, right? Because absolute value doesn't tell us direction, it just tells us distance. And so it could be in the negative direction up to but not including 3. Does that make sense?
Yeah.
And then it could be any of these numbers in between, right? So we would shade like that. What does that look like that we've just been doing, Tessa?
But it couldn't be 0, right?
No, it could be. X could be at 0. Because then it would be a distance from 0 less than 3. Okay, so x could be 0. But what does this look like that we've just been working on?
It looks like an and.
It looks like an and graph. And that's exactly the way we would end up graphing or writing the final solution. We would write it as -3 is less than x and x is less than 3. Okay, so our final written solution would look like that. The way that we would end up solving this comes out to be a little bit different. Whenever you have absolute value involved in your inequality, you've got to consider the possibility that it could be negative. It's written as a positive, but it could also be negative. So x is less than 3 is obviously one way we could write it. But when you think about this half of the final inequality, how would we write that? X is greater than -3. And so what we see here is we start with the original inequality, x, the absolute value of x is less than 3, and we just write that without the absolute value brackets. And then we rewrite it with x and then flip the sign and make the answer negative. Okay? That's going to be a pattern we follow over and over. And what they're called in the book is case 1 and case 2, because we've got two different cases here. Case 1 could be that m plus 2 is less than 11, right? And we know how to solve that. Just subtract 2, and m is less than 9. But it could also be what? Case 2. Yeah, it could also be the case that m plus 2 is greater than -11. Flip the sign, make the answer negative. Subtract 2, and m is greater than -13. And so if we were to graph that and write our solution set, we have the small number to the left, that's -13. We have our big number on the right, that's 9. 0 would be somewhere about right there, right? And so we'd have an open circle at -13, an open circle at 9, shade everything in the center, and then we could write our solution set, the set of all m such that m, whoops, I don't want to start with m. Set of all values for m such that negative 13 is less than m and m is less than 9. So we have case 1. 2n minus 8 is less than or equal to 2. Add 8, so 2n is less than or equal to 10. Divide 2, so n is less than or equal to 5. Case 2 is going to look like what? Greater than or equal to negative 2. Add 8 to both sides, so 2n is greater than or equal to 6. N is greater than or equal to 3. All right, so it just says graph. We won't worry about writing solution set this time. How's that? So graph it. You have a 3. You have a 5. Both ends get closed circles. And graph in the center, right? You would need to write, you do, even though we're not going to write it in set notation, we do still need to write the final solution as 3 is less than or equal to n, and n is less than or equal to 5. Okay? Ooh, what's different about this one?
It's an absolute value.
Think real hard about what this says for a second.
It's already negative.
It's already negative, okay? What do I know about absolute value, though?
It has to be greater than the distance. It has to be positive, right?
Ah, yeah, what is the absolute value of negative 1?
1.
It's positive 1. What is the absolute value of positive 1?
1.
So absolute value always yields a positive, right? So is it possible that the absolute value of any number or any value can be less than a negative number?
You'd have to have an outside variable constant.
As it's written, is it possible
No.
that this could be less than negative 3?
No.
It is not possible. This is a no solution. Anytime you have absolute value with a less than sign and then a negative number, it's got to be no solution. We'll talk more about greater than signs here in just a second. But this is always going to be a no solution if it's in this configuration, okay? All right.
Mr. Fish,
Yes,
could you send Adriana Villalobos to the guidance office with her things?
sure.
Thank you.
All right. Next, let's consider this. The inequality x is greater, the absolute value of x is greater than 3 means that the distance between x and 0 is greater than 3, right? So wherever x is, x has to be further away from 3 in this direction, or further away from 0 than 3 in this direction, or it's got to be greater than 3 away from 0 in this direction. Remember, it doesn't tell us which direction, it just tells us the distance. So the distance has to be greater than 3. So our OR statement would look like x is less than negative 3 or x is greater than 3. Okay? So we're still going to have case 1 and case 2. They're just going to look different this time. It's going to be an or statement instead of an and statement, okay? All right, so let's look at this one. 3n plus 6 is greater than or equal to 12. So case 1, 3n plus 6 is greater than or equal to 12. Subtract 6. 3n is greater than or equal to 6. Divide 3, n is greater than or equal to 2. Okay? Then we'd have case 2. So 3n plus 6 is less than or equal to negative 12. 3n is less than or equal to negative 18. Divide 3, so n is less than or equal to negative 6. So you have negative 6 here, 2 is right here, 0 is about right there. You'd have closed circles at both places. N is less than or equal to negative 6, so it's got to go to the left. Or n is greater than or equal to 2, so it's got to go to the right. Okay? Aiden?
Is there any possible way for n to be greater than 2 and n to be greater than negative 6 on this type of problem?
That is a great question. Let's move on and see if we answer that. 2k plus 1 is greater than 7. So we've got case 1. So case 1 we'll just do right here. Case 1, add 1 to both sides. Or no. Sorry, subtract 1 from both sides. So 2k is greater than 6. So k is greater than 3. Case 2, 2k plus 1 is less than negative 7. Subtract 1. 2k is less than negative 8. So k is less than negative 4. Graph it. Negative 4 is here. 3 is here. Both sides get open symbols. K is greater than 3, so it goes this way. Or k is less than negative 4, so it goes this way. All right? R minus 6 is greater than or equal to negative 5. Now, this is different than with the and statements a minute ago. Because think of it, with or statements, we only have to make one of them true, right? And so if this is going to turn into an or statement, we still got to solve it and see if one of the statements is true. It might be that only one of them is true and the other one can never be true, but that's all right because we can still make one of them true. All right? So we still need to do case 1 and case 2. Case 1, we would add 6 to both sides, correct? So R is greater than or equal to 1. And then case 2, R minus 6 is less than or equal to positive 5. Right? I did that right. Okay, switch the sign, make it positive. So add 6. R is less than or equal to 11. Okay? So we have a 1 here. We have 11 here. Both of them get closed dots, right? So this one says R is greater than 1, so it shades this direction, right? Okay, and think of it, what if R is 12 right here?
It can be.
Does that make this one true? Yep, so I can keep shading this direction. And R is less than 11. So what if R goes to 0? Is that okay? Because 0 is less than 11, so that makes that one true. And so this, Aiden, I think answers your question.
I had somewhat like,
Okay,
say R is greater than 1 and R is greater than 11. Like, could you somehow get that with two pieces? Like equals
oh,
real numbers?
no, because you're always going to flip the sign. You're always going to have an R is greater than and an R is less than. Because you have to flip the sign. All right. Well, actually, no, because it would be the same in both cases. If we, I think you'll see some of this on your homework, but well, hold on just a second. Let's finish this one. So this, the solution set is all real numbers. Okay, and that's the way you would write the answer there. So R, you would still write out your inequality, R is greater than 1, or R is less than or equal to 11, but you need to understand that that means all numbers meet that requirement, okay? As far as, Aiden's question, I don't think you can ever, I can't think of an occasion where you would end up with both the signs facing the same way. In this scenario, using absolute value. Okay, if we come across that, that'll be a surprise to me. We'll just work the assignment for now. The assignment, I forgot to make a slide for it. Assignment is 5.5 practice worksheet.
Yes.